Okay, so in the warm-up there, so we're going to extend what we did yesterday. So we're going to be using Venn diagrams and frequency tables, similar to some stuff that you saw before. We're also going to add what's called the addition rule to this. Okay, and that one's kind of interesting. There are ways to get around it for simple things. For more complicated probability issues, then you definitely want to know the addition rule. And if you rely on the addition rule today, it's going to make more sense as to why we use the rules we do over the next couple days. We got 2 more sections to cover next week. So what's the difference between an event and a sample space? Can somebody raise their hand and tell us what the difference is between an event and a sample space? Yeah.
Doesn't the event happen inside the sample space?
It does. The event has to be inside the sample space. Anybody else want to try, Luke?
An event is one specific thing, and
Very
the sample
good.
space is the collection of all of the things.
Excellent. So we're going to say for an event, it's one specific outcome. Now, that outcome can have more than one thing in it, but we describe the one thing that we want to have happen. And what did you say for sample space?
All of the things.
All of the outcomes. All outcomes that are possible. Okay? All outcomes together. Okay? And then what's the difference between a union and an intersection? So if I were to do a union, I'm going to put a union like this. Sometimes it can be helpful to describe them with a picture. So that's a union, and that's an intersection. All right? So if you had to put words in that, how would you describe a union? Crew?
All of it.
Okay. So in either, all of it.
Oh yeah.
Okay. So we'll put all. So it's got to be an either. And then what about an intersection? Luke?
Both.
In both.
Mostly yeah.
Okay. And just a reminder, when we do an intersection, we use this, and we use an and as the word for those, because and kind of means both or. And then this one, we use an or, and that's a union. We put all of them together. So if it's in one or the other or both, then that's totally okay. Okay. What about independent events? Yep.
One event doesn't affect the other.
Very good. Doesn't affect, effect, impact the other.
Effect or defect.
Yep. So affect is influence. Effect, I think, has an effect, has an impact. A lot of people will just say impact rather than that. All right. So in the last lesson, we talked about Venn diagrams. We've looked at frequency charts before. Both of those are ways to organize information, and we talked about the fact that when we look at data and statistics, we want to be good consumers of information and good presenters of information, and we've got to look at it carefully so we know, hey, what's going on here? What does this actually say? If we kind of browse through it and say, I think I get it, then we're probably going to end up making mistakes, okay? So we found some joint probabilities yesterday. So the joint probability of flipping a coin and rolling a die, those are independent. If they're independent, then we can use the multiplication rule for this. So for example, here we have the probability of flipping a head and rolling a 3. So that's going to be 1/2 for the head, 1/6 for the 3. So we end up with 1/12 altogether. There's the answer for that one. Okay, so we're doing 2 completely separate things. They are independent of each other. Okay, and we can use the multiplication rule in order to get that. So that is an intersection. Okay, that is an and, the word that describes that. If we're finding joint probabilities for independent events, those are pretty easy. But if we've got a union, then it's more difficult. Okay, so if we've got something like this is called the addition rule. And I'm hoping by showing an example of this, you'll see why the addition rule works the way that it does. So this is the probability of A or B happening. That's the probability of A plus the probability of B, and then we have to subtract off the probability of the intersection. So I'm going to change the problem that we did up above. Okay, this was an intersection. This was an and. This is an or. Okay, so this would be a union. The union of the two things happening. So a head can happen, okay, or a 3 can happen. So this is going to be the probability of a head, which is 1/2. The probability of a 3, which is 1/6, and then we're going to subtract the intersection. Well, this was the intersection right here, So that's going to be, we're going to subtract 1/12. And then we've got to do a little bit of arithmetic. So since the denominator of the biggest one is 12, we're going to do this. I'm going to do 6/12 plus this would be 2/12 minus 1/12. So this is going to be, add them up, that would be 8/12 minus 1/12, that would be 7/12. So the answer on this one is 7/12. Okay? Now, I'm going to show you an example of this. There are some problems just like this one, and you can see why it is this way, why we have to subtract off that little intersection. There's some examples like that or problems like that on your assignment. We're going to look at a different one, this one right here. So this says, we've got the same ones. We've got Megan colors and Jack's colors. Okay, we want to find the probability of Megan. So the probability of Megan's colors are, how many colors altogether? There are 8. How many colors are Megan's? 4. So her probability is 1/2.
I know half of
Probability of Jack? Again, 8 outcomes in the sample space altogether.
trace.
Jack has 3 colors. So that doesn't reduce at all, so that's going to be 3/8. For the intersection, that's an and. They've got to be in Megan's color palette and Jack's color palette. So that means there's only 2. So this is 2 out of 8. And we can reduce that to 1/4. All of those are pretty darn easy. Okay, now, the next one is actually pretty easy also, but I want to figure it out 2 ways. So this is the probability of Megan union Jack's color palette. There's still 8 altogether, right? How many are in the union? Yeah.
5.
There are 5. Okay, that's the right answer. I'm going to change colors here, and let's talk about why. Fellas, watch. You need to pay attention. This is more important than the pencil. You would think that if you're just going to union those together, put those together, that it's going to be this plus this. It's going to be 1/2 plus 3/8. Or in other words, it's going to be these two added together. If you add the 2 of those together, you can see that it ends up being 7/8.
That's a lot.
This is impossible.
But the right answer is 5/8. Say that again? Counted red and white twice. So in order to get this one, if we did the probability of Megan, we did those 4. If we did the probability of Jack, we did those 3. And what happened here? We counted the intersection twice. So here's why, in order to calculate unions, we have to do this. It's the probability of the first one, which would be 4/8. Probability of Megan is 4/8. Probability of Jack's color palette is 3/8 minus the intersection. That's going to be 2/8. And then in that case, we end up with the right answer of 5/8. And down below, here's why we have to subtract the intersection. And you're going to see a couple of these again on the assignment. Why do we need to subtract this intersection, adding the 2 separate ones? Somebody said it earlier. It's so we don't count the intersection twice. We don't want to count red and white here with Megan and red and white here with Jack. We just want to count all 5 of those together. So we do Megan's colors, Jack's colors, subtract off the ones that are in the intersection, and then we've got the right answer. Slightly more complicated, but we can handle that. But we do need to make sure that we're paying attention here. So this is a frequency table. The joint total is 33. This was chores and curfew. So this is people that had yes chores, no chores, yes curfew, no curfew. And we can identify every one of these in here and we can describe them. So I'm going to ask Mason just to make sure we're in good shape. Mason, for this one right here, how would you describe those 3 people?
They have no curfew and they don't do chores.
They have no curfew and they have no chores. Remember, it's a 2-way frequency table because you can describe each piece of data 2 different ways. Everybody good there?
Me.
Okay, so we want to find some probabilities now. Probability of yes chores. Outcomes in the sample space 33.
25.
Yes chores. Hold on. What is it?
20. Wait. Oh, 18. Yeah, I was looking
Okay.
at curfew.
We got to find the right one. So we're doing this by rows. So if we're talking about chores,
Oh,
chores
yeah.
are the rows.
18
You want to
over
find
33.
yes for chores, come over
I know
here.
that.
So it's going to be 18 out of 33.
Yes, sir.
Luke, what should we do?
Simplify.
Very good. So this is going to be 6 out of 11. There's our answer. Next one, probability of no curfew. We're talking about all 33 people all together. No curfew. You got it?
It's gonna be 8.
It is, because we're looking at the curfew. Now we're looking at the columns. People have no curfew. If we add them all up, if we ignore whether or not they have chores or not, it's going to be 8 over 33. 8 over 33 doesn't reduce, so we circle that and we're done. Next one. Yes curfew, intersect yes chores. So these people have a curfew and they have chores.
Wait, that one's in.
Zach, what do you think?
13.
It is 13 because there's the intersection of the two of those. Okay, so that's going to be 13 out of
Yeah.
33. That doesn't reduce, so we're just going to circle it. Okay, this is our first union. Here's our first union. Yes chores, unioned with no curfew. Yes, they have chores, or they have no curfew. Yes, they have chores, or they have no curfew. D, what do you think?
It's just 6 11s again.
You think it's 6 11s? How'd you get that?
Because if you look at the graph, when it says 13 for the yes chores, and that you have to go horizontally. And for chores it says yes, but in the no aisle there's also 5 in the same row, so therefore when they add up to 13. Well,
What the heck?
what?
I think it's.
This is why, depending on how you look at things and how you explain probability, it can be kind of difficult. Colson, what do you think?
So it's not that because there's 18 who have yes chores, but there's 8 who have no curfew.
Mm-hmm.
Whereas he just thought it was 18 out of 33.
Okay. All right. Let's take a look. Let's see what happens here. So this is going to be yes chores. Okay. So let's find the probability of a yes for chores. Whoops. And we should have done different words here. So we're going to find the probability of yes chores.
18.
Okay. What is that?
Yeah.
That's 18 out of 33. And then the probability of no curfew. What's the probability of no curfew?
8 over.
8 out of 33. So we're going to add those together. Whoops, 8 out of 33. Okay? And then we have to subtract whatever their intersection is. Okay? So we want the intersection of yes chores and no curfew. So yes on chores, no on curfew. We're going to subtract how many? 5. So we're going to subtract 5 out of 33. So this is going to be 26. That would be 21, right?
1 over 13.
21 over 33. Luke, does it reduce?
Yes.
7 out of 11, right? Correct?
It does? Oh.
3 goes into both of those.
Oh, yeah.
Okay, everybody good with that? Okay,
Yes, sir.
I want to see if we can figure out what's going on here. So here's yes chores. Here is no to curfew. If we just add those two numbers together, if we take 8 and 18 and add them together, we get 26. But what happened right here? We counted the 5 twice, so we don't want to do that. That's why we subtract that off. Now, could you do that visually and just say, yeah, I already counted it here in the 18, so I'm not going to count it there. I'm only going to add 3, so that gets me to 21. I think that's what Colson is saying. All right, everybody good there?
Ah.
See why we have to subtract that off? Okay, don't say anything out loud. Would you just find the probability of yes curfew? Check with your neighbor. Raise your hand if you want to tell us what it is.
25 over 33.
It is 25 over 33. Pretty simple one right there. Whoops, make that look like a box. No chores. Find the answer, check with your neighbor. Check with your neighbor.
5
Make sure you write it the right way. Raise your hand if you want to tell us. Keely, what do you got?
5 11.
5 11s. How'd you get 5 11s?
You go to the no chores, you
Mm.
have 15.
No chores, yep, so it's gonna be 15 out of 33, and that's gonna reduce to 5/11ths. Okay, last one, do not say anything out loud. This is an or. No chores or no curfew. Do it yourself, no chores or no curfew. Who wants to raise their hand and tell us the answer? Luke, what do you got?
20 out of 33.
20 out of 33?
Yeah.
Okay, let's check and see. I'm gonna do it a couple different ways. Probability no chores. No chores was right here. That was 15/33. Plus the probability of no curfew. No curfew was up here. That was 8. So we should be able to do that. Okay, and then we're going to subtract off probability no chore and no curfew. We didn't have an intersection there, so we're going to have to figure that out. No chores and no curfew. That's going to be 3, right? So we're going to subtract off 3 out of 33. So this is, let's see, yep, 23 minus 3. So that's going to be 20 out of 33. Got the right answer. Okay, raise your hand if you got that. Okay, another way to do it, we could do it on the frequency table, but again, we want to understand the rules and rely on those. No chore. So no chores would be right here. Whoops, all these guys, let me make this look right. No chore would be right there. No curfew would be right there. So we're going to add the 2 of those numbers together, but we're going to subtract off the intersection so we don't count it twice. So 15 plus 8 minus the 3. Same answer as we got right there. Any questions? All right, flip the page over. Okay, last little thing we're going to talk about. Okay, until next week. Tomorrow we're going to do a review. This is using a two-way table to answer a couple questions about this. This is about independent events. Now, you're going to need your calculator for this, so get that fired up. This is how we tell whether or not 2 events are independent. If we're doing things separately and we can tell for sure that they're independent, that's pretty easy. Rolling a die, flipping a coin, they don't have any impact on each other. Drawing marbles out of a hat where we replace the colored marble every single time, that would be independent. Okay, they don't impact each other. Okay, but if I draw it out, I keep it out, that's going to change the result every time. There are times where the data gets really, really complex, like it is here, and we've got to rely on a rule in order to tell us whether or not they're independent. And here's the rule for independent. We can tell whether or not they impact each other by this. If we take their individual probabilities, multiply them together, and it's the same as the probability of their intersection. So here's what we're going to do to figure this one out. We've got this data that's sitting right here. It's just a two-way table, and it says probability of being male. So there are 1571 altogether. Male, 832. If you want to come up with a decimal for that, that's fine. You don't need to right now. Probability in 10th grade. So 1571 is the joint total. 10th grade, 605. Probability of both of those happening together, so their intersection, male and in 10th grade, is going to be this. Male and 10th grade, the intersection is going to be 320 over 1571. So here's the question. Does this times this equal this thing right here? Now, if you want to do it in fraction form, go ahead and do it in fraction form. If you want to do it in decimals, go ahead and do it in decimals. Okay? Take those 2 fractions, multiply them together. Does it equal what you get for the other fraction? And again, if you want to do decimal-wise, that's totally okay. So I'm going to shrink this down. I'm going to quit here. I think I multiplied the two of those together successfully. Their intersection is 320 divided by 1571, and I get exactly the same thing.
No.
So the answer here is, yes, those are independent.
Well, it's
It's
like
not this,
slightly different.
yeah, they're slightly different. if that
Oh, you're
matters.
right. Ooh, that's interesting. Oh, did I hit something
No,
wrong?
because that's what I got on mine too.
Same thing? Ooh, so are they exactly the same?
No.
Ooh, they're not. So what's the answer going to be? The answer on this one's going to be no. Okay.
Is this supposed
Is
to
it
be no?
supposed to be
Okay.
yes?
Did I get all the right numbers here?
Yes.
Okay. I didn't make a mistake in grabbing numbers.
What if you added
Okay.
wrong on the table?
Well, this was a photocopy of it. Well, it was a screenshot of another thing. So I'm assuming that we did the numbers right, right? Okay, so this is a no. Let's check and see. So I'm going to draw a line right here. Let's check and see if being female and 12th grade is independent. So we need to figure out first probability of
Being a female.
female, probability of 12th grade, and then we want to find the probability of being female and being in 12th grade. We want to find the probability of their intersection. So let's see, female. 739 over 1571.
Yes.
12th grade. 431. And their intersection.
216.
216. So we'll grab those and we're going to take, I'm going to do this. Maybe it's easier, I don't know. Independent?
No.
Nope. Okay. So here's what's interesting. Okay. I modify other examples. I swear they used this one in years past and that first one came out to be right, but I think we did it right and we got a no. Okay. Now, when you have stuff like this, I mean, do we really think that the gender would have anything to do with what grade they're in?
No.
Probably not. We would assume that those are independent. Okay. Or sorry, they're
Yeah, independent.
dependent in this case. Okay. So we're going to go with this. I'm going to double check. I want to show you some